All right, calculus students, continuing on section 5.4. So we want to look at an implicit differentiation problem dealing with exponential functions of order e. And so I want to find dy dx of this implicit equation. And so what I'm going to do, as you know, when you're doing implicit differentiation, we're going to take the derivative with respect to x of each term. So I've got the derivative with respect to x of e to the power x times y plus d dx of x is equal to d dx of y squared. Okay, the first, the ones on the right-hand side are easiest to do. So here the derivative of y squared with respect to x is using the chain rule. It's going to be 2y times dy dx. And then the derivative of x with respect to x is just going to be 1 times dx dx, which is also 1. So this is going to be 1. And so the only one that's kind of tricky here is this guy, because we have the form of the derivative with respect to x of e to the u, which is going to be equal to e to the u times u prime. Okay, so in this case, our u is going to be x times y, and then u prime is going to be the derivative of x times y. Now, x times y, we're going to have to use the product rule. So it's going to be the derivative of x, which is 1, times y, plus x times the derivative of y, which is dy dx. And so using this rule, then, this first term becomes e to the u, which is e to the xy, times u prime, which is y plus x times dy dx. And I'm going to bring all these down. So it's going to be plus 1 is equal to 2y dy dx. Okay, so now it just becomes an algebra problem. And so I'm going to use purple this time. All right, so I'm going to multiply this out. So I get y e to the xy plus x times e to the xy dy dx plus 1 is equal to 2y dy dx. And remember with these problems, the next step is we want to get everything with a dy dx onto one side. So I'm going to bring this guy over here, and then I'm going to flip the equation. So and factor out the dy dx. So I've got 2y minus x e to the xy dy dx is equal to y to the e to the xy power plus 1. And then the last thing, I'm going to divide both sides by this term, and I get dy dx is equal to y to the e xy plus 1 all over 2y minus x e to the xy. And that's it. And so use implicit differentiation normally. Just remember we only have this new rule. The derivative of e to the u is e to the u times u prime. Okay, let's see. Next. Okay, so next we want to look at integration of e to the x and e to the u. And this is relatively simple to memorize because the derivative of e to the x we know is e to the x, and the derivative of e to the u is e to the u times u prime. So let's first start off with, we know already that the derivative of e to the x is just equal to e to the x. And so what I can do is I can multiply both sides by dx, and I get d e to the x is equal to e to the x dx. And so what I'm going to do is I'm actually going to kind of flip this. So what I'm going to do is I'm going to write this as e to the x dx is equal to d e to the x. Okay, and so if I differentiate both sides, oh no, sorry, if I integrate both sides, because we want to integrate. So if I integrate e to the x dx is equal to the integral of dE to the x. Remember that the integral of d to the anything, or d of anything, is equal to that thing plus c. So we got a pretty simple rule for integrating e to the x. So the integral of e to the x dx is just equal to e to the x plus c, which makes sense because the derivative of e to the x is e to the x. All right, let's do the derivation of the integral of e to the u. So we know that the derivative with respect to x of e to the u is going to be equal to e to the u times u prime. Well, and remember that u prime is just du dx. So this is d dx of e to the u is equal to e to the u times du over dx. Okay, I'm going to push pause because somebody's like doing a weed whacker right outside. I'll be back when they're done. All right, we're done with the weed whacking. All right, so anyway, so here, what I can do is I can multiply both sides by dx, and if I do so, then these cancel, and so then what I get is and I'm going to flip this around. So I get e to the u du is equal to d e to the u. And now what I'm going to do is I'm going to integrate both sides. And remember that d to the anything is that thing plus c. So what I've got here now is another rule, which is the integral of e to the u du is just equal to e to the u plus c. All right, so relatively simple rules. This is one of the reasons I like dealing this particular section, because the rules for the derivatives and integrals involving e are relatively simple to memorize and to work with. Okay, let's do some examples. All right, the first example is let's do the integral of secant squared of x times e to the tangent of x dx. Okay, so here, if I look at this, I'm going to have the form of the integral of e to the u du, which is equal to e to the u plus c. Okay, oh my goodness, the weed whacker's back. Like, why don't you go back and forth instead of a long line? It doesn't matter. I'll be right back. All right, we're good now. All right, hopefully that'll be the end of it. All right, so where we were at is we still have this form. We've got e to the u, and you're always kind of looking for that, like e to the u, and then you're going to need a du. We know that the derivative of tangent is secant squared, so hopefully you can kind of see that we've got this u du combination. But to make it a little bit easier to see, I'm going to rewrite this, and I'm going to write this as the integral of e to the tangent of x times secant squared of x dx. Okay, so now I'm going to start my u substitution. So I'm going to let u be equal to tangent of x. So now I've got my e to the u. And then the last thing I need to do is I need to substitute the secant squared x dx. And to do that, I'm going to come down here and differentiate u with respect to x. So du is going to be equal to secant squared of x dx, which is exactly actually what I have here. So this whole thing is just my du. So that's kind of makes things a little simpler. So now I've got the integral of e to the u du, which is just equal to e to the u plus c. And then my last step here is I'm going to put my u back in. So I've got e to the u, and my u is tangent of x, plus c. And you can, like any antiderivative, you can verify that this is correct by taking the derivative and seeing if you get, if you take the derivative of this, you should get what's inside the integrand, and you would using the rules that we learned in this section. Okay, next example is, let's do one that looks a little more tricky. but isn't going to be too bad. So let's do the antiderivative of e to the power square root of x over the square root of x dx. And I still have my form in this case. The form is going to be equal to the integral of e to the u du, which is e to the u plus c. But in order to see this a little bit easier, I am going to separate this out. So I've got e to the square root of x times 1 over the square root of x dx. Weed Whacker's back, and I'll be back. All right, back. All right, so I'm going to let u here be equal to the square root of x. So that gives me my e to the u. So what I have to do to complete my substitution is get this 1 over square root of x times dx in terms of u. So I differentiate my u. So du is 1 over 2 square root of x dx. But I only need this 1 over square root of x dx. So I'm going to rewrite this as du is equal to 1/2 times 1 over the square root of x dx. And I'm going to block off what I need to make my substitution. And if I solve for that, then I get 1 over the square root of x dx is equal to 2 du. So if I put that back up here, this is 2 du. So now I can write this as this is equal to 2 times the integral of e to the u du. And so if I look up at my form up here, then it's going to be, I've got 2 times this, so it's going to be 2 times e to the u plus c. So this is equal to 2e to the u plus c. And then I just have to put in my u. That's my last step. So u, in this case, was the square root of x. So this is 2 times e to the square root of x plus c. And you can verify that this is correct by taking the derivative and seeing if you get the integrand. Okay, one more example. No, actually, I'll do a couple more examples, but one more big or longer example. Okay, so for this example, what we want to do is let's look at a definite integral. So let's say I look at the integral from 0 to 1 of e to the x all over 5 plus e to the x dx. Okay, now here, if I want to look at the form, this is going to be a little more tricky. But I've got an e to the x on the top and an e to the x on the bottom. And I can't factor this in any way because I've got 5 plus e to the x in the denominator. So this is a little tricky, but this is actually a u substitution problem. And it's going to be in the form, which you may not see right away, but this is actually in the form of the integral of 1 over u du. And the integral of 1 over u du, I know, is the natural log of the absolute value of u plus c. Now, in order to see this a little bit better, I'm going to rewrite this integral. And if you get tripped up when doing these and you're not sure what to do, you can kind of write it like this and see if that helps. So I've got 1 over 5 plus e to the x times e to the x dx. Okay, so let's see how this u substitution works. This is kind of a common problem. There's several that are similar to it on your homework. So I'm going to let u be equal to what's in the denominator, which is 5 plus e to the x. And that gives me my 1 over u. And so what I need to sub is this e to the x dx. Now the cool thing is that when I take the derivative du, then the derivative of 5 is 0, and then the derivative of e to the x is just e to the x. So du is equal to e to the x dx. And that's what I need to sub. And so this e to the x dx is my du. And so you can kind of see when you have like an e to the x over something plus or minus e to the x, or even like e to the 2x over something plus or minus e to the 2x, then you want to use this particular form. Okay, so what I'm going to do is I'm going to rewrite this in the form. So I got the form, and remember we're going to have to change our variables here. So we want these the interval of my integration to be in terms of u, not x, and I'll deal with that in a moment. So this is the integral from 1 over u du. Okay, so now I'm going to change my variables. And so I know that u is equal to 5 plus e to the x. So when x is equal to 0, which is my lower point on my interval, then u is equal to 5 plus e to the 0, which is going to be 5 plus 1, which is 6. And then when x is equal to 1, then u is going to be equal to 5 plus e to the 1, which is just 5 plus e. So I'm going to put that back over here on my definite integral. So this is u is equal to 6 to 5 plus e. Now remember, e is 2.71 dot dot dot. So 5 plus e is greater than 6. But if you weren't sure, it doesn't really matter, because remember, mathematically, if 6 happened to be larger than 5 plus e, and you did the integral, you still get the right answer, because you don't have to flip it. But in this case, we're not going to flip it because 5 plus e is greater than 6. Okay, so now I just carry out the first fundamental theorem of calculus. So the antiderivative of 1 over u, I know, is the natural log of the absolute value of u, and I'm going to evaluate that between 6 and 5 plus e. So that's going to be equal to the natural log of the absolute value of 5 plus e minus the natural log of the absolute value of 6. Now this isn't simplified because I know that, okay, first of all, when I've got natural log of 5 plus or minus something, or something plus or minus something, there's no rule. You have to leave it like that. However, if I've got the natural log of something minus the natural log of something else, then I can use the rules of or properties of natural log to simplify that. And so as for my answer, then I'm going to write this as the natural log of parenthesis. I'll tell you why I'm putting a parenthesis in a second, of 5 plus e all over 6. And so there's your final simplified answer. Now, the reason that I dropped the absolute values is because I know that e is positive and 5 is positive. So 5 plus e is a positive number, so these absolute values are no longer necessary. And I know 6 is a positive number, so these absolute values are no longer necessary. So therefore, that's why I wrote this in parentheses here. And so this is the preferred form, as long as you know what is inside the absolute values. Okay, there's a couple other quick points I want to make before we end this section. Okay, and that is this. Remember, I talked about this at the very beginning. We started covering Chapter 5, but it's worth mentioning. I'll show you kind of where it's used. And so recall that if I have e to the natural log of u, then that's just equal to u. And if I have e to the natural log of u to the a, that's just equal to u to the a. However, if I have e to the a natural log of u, this does not equal, so be careful, this does not equal like a times u. What you have to first do when you have something like this is you have to bring whatever's in front of the natural log up as an exponent, and then you can use the rule that e to the natural log of anything is that thing. Okay, so let's see where kind of this shows up, and sometimes they'll put problems like this on the AP test, just to make sure you know these properties. So the first one's relatively simple. So let's say I have the integral of e to the natural log of x dx. Okay, so instead of using the integration rule, and you'd actually come up with the same answer, it's a lot easier if you just recognize that e to the natural log of x is just x. So this integral is actually equal to the integral of just x dx, which is x squared over 2 plus c. And then the last example is, let's say I have the integral of e times 3 natural log of x dx. Now, this is not equal, absolutely not equal to the integral of 3x dx. Nope, 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 nope. And the reason why is because the rule says, or the rule is that e to the natural log of something is that thing. But if there's something in front of it, like this 3, I have to bring this 3 as an exponent up on the x before I use that rule. So in order to solve this one, I'm going to rewrite this as the integral of e to the natural log of x cubed dx. Now I can use that rule, and the e to the natural log of x cubed just becomes x cubed. And so this just becomes the antiderivative of x cubed dx, which you know is x to the fourth over 4 plus c. Okay, so that concludes section 5.4. And we've got one more section that's a pretty quick one, and that's it. All right, I will see you in that video.